Today we are going to do section 7.2, but before that I want to show you the answer sheet again. Let's see, why is it moving there? And just for no reason, okay? And especially the part about chapter 7, which we've already finished the first part. I mean section 1. Good enough. Anyway, so that is that. So here is the previous page that we already scanned. Just want to show it to you again for convenience. Mostly just this part, okay, the new part. That should be clear enough. Next, page 224 and 225. Did I forget to put the pink slip out? Yeah, I think so. Okay, I'll do that in a second. Let's see. Okay, a little bit closer on top. And a bit closer on the bottom. That's good enough. And finally, 226 and 227, the homework page. Okay, let's see. And then a little closer on top. Is that not flat or something? Give me a second here. Well, try again. Still not flat. Let me fix that. All right, try again. Let's see. That looks vaguely better, I guess. Okay, a little closer on top. And on the bottom. Let's see. Okay, that should do it. All right, so let's start on section 2 of chapter 7, Green's theorem, on page 223. First, please read this little introductory paragraph yourself, and we're going to start right here. If a region is bound by one or more curves, the positive direction over the boundary, the one that leaves is the one that leaves the region to the left. Okay, so imagine walking around the boundary. So then the direction that's positive is if your region is on your left. Yeah, okay. So for the region between two concentric circles, then the positive direction will be counterclockwise when you're on the outside and clockwise when you're on the inside. Okay, just imagine yourself walking along there. So anyway, so that is the sense of the positive, in the positive sense. Generally speaking, we only think about the boundary on the outside so much. So then generally we're considering going around counterclockwise. And that's if you know what how the clock runs. Okay, nowadays we don't use the analog clock as much, so the word clockwise might not mean a whole lot. But anyway, imagine the clock is well, whatever. Figure out how the clock goes. Anyway, so then let's look at theorem 2, where this is the Green's theorem, which was covered in Calculus 3, but we're going to rebuild this thing from the ground up. So R is a region Rx and also Ry. That's important, okay? And tau, sorry, gamma. My brain gets stuck on tau. Whenever I say tau, think gamma. Gamma is the boundary of R, okay, and then P and Q are some C1 function in R. Then this interesting and familiar relationship exists, that is integral of P dx plus Q dy on the line, on the boundary, is equal to the double integral of the interior of Q1 minus P2. All right, and when the line integral being taken in the positive sense, that is counterclockwise. Now first I want to mention quickly the kind of region that is Rx and also Ry. So I have scanned the book into the computer here so you can see it. I can explain a little better. So let's start with the first part, which is the short part, okay? Now remember the region is both Rx and Ry. Now did I show you how that might be possible? I think I forgot. Give me a second here. Now I have drawn some quick simple examples here. Regions where R equals to Rx and also Ry. Besides the obvious rectangle, you can have parallelogram, triangle, circle, trapezoid, ellipse, and some kind of hexagon or other multi-sided thing. Okay, and you can probably think of other more complicated examples, but that's just to show you that it is possible for this to happen. All right, so so now that we know Rx can also be Ry in not just a rectangular shape, let's consider a theorem to chapter 6, which indicates that the double integral is the same as the equals to the iterated integral. That's just the fundamental theorem that I will show you quickly here. Okay, and yeah, this is page whatever. See, the double integral equals to the iterated integral. So then, knowing that, then we can then calculate, being that this is P2 right here. If it's P2, then it's the second derivative that's taken with respect to y, so we can just apply the fundamental theorem, and which equals the top, okay, subtracted by the bottom. So far, so good. Now, the next part of the proof, the book gave very little explanation, which is why I expanded it somewhat here, that I feel would give a better situation of what's going on. Now, from page 220, equation 4, I copy and pasted it here. So we have, say, we have a function where let me first show you the page, I guess. So here's page 220. As you can see, and next to equation 4, we have, let's see, is up there. But anyway, next to equation 4, we have we let phi of t equal to t, okay? And psi of t is now continuous rather than differentiable. Then in that case, we have then the integral over gamma of f is the same as f of x phi of x dx. The reason for that, as I've copied that sentence down here, is because first we just plugged it in. The phi of t equals phi of t is substituted as t, okay, right here, and then psi of t stays itself. So then the integral of if you plug everything in, then and dx is x is phi, so then dx it will become just dt, and that's how this equation goes. Now the second part of what we're going to do here is we're going to change the variable, the dummy variable in here, which is the t's, we'll change it into x, and nothing changed here. So then this equation also equals to the integral of x phi of x dx, and I think that is also what the book says. Let's see. Yeah, see, this is also equation 4, as you can see there, and in the middle of the screen. You see equation 4, where the integral of over gamma of fxy dx equals to f of x phi psi of x dx. Okay, now at this point, it's extremely important to figure out what is the curve that we're integrating over. That is, I said that the curve in this case, I marked it very carefully, the curve is gamma 1, okay, which goes from t to psi of t. That is, in the graph, I graphed the sample here. The graph is the blue line, okay? It goes from this point down here to this point up here, or something like that. It's just something I made up. This is gamma 1. That curve, only the blue part, that is that curve is gamma 1 is the psi of x, okay, and that is where our definition makes sense. That is to integrate some function f over gamma 1 from one end to the next, okay, is integrating from a to b. You plug in this function, which is the same as this, where gamma 1 is being parameterized as t comma psi of t, or just psi of x, okay? Is the same deal. So then, and similarly, if we have another curve, a different curve, which is by substituting y equals, and by substituting y in a similar way, we'll let psi of t equal to t. So then this is becomes let's see, did I get this right? Let me think. Yeah, it's correct. Okay, this is slightly confusing, so I have to be very careful. So the point is, gamma 2 is the function phi of x, where that's, in other words, the bottom curve, and then integrating over gamma 2 will be equal to, is where where y value will be equal to phi of x, okay, and this, all this is working out in the same way. Where over the region, this region here is called the Rx region. We also have a vertical line here. There's a gamma 3 and gamma 4. They are perfectly, they're just vertical lines. So then, okay, now I want to be very, very clear on this. Okay, this is important that we know which line we're integrating over. And like, what are we talking about here? In other words. So next, we are going to integrate around the entire border of our x. Okay, the entire border consists of gamma 1, 2, 3, and 4. Right? So then we'll start at, so integrating the function f over the entire boundary of our x will be equal to, as we can see here, there's gamma 1, which is going down, which is y is negative. Okay, gamma 1 going down, negative, and then and then go down gamma 3. We're just going counterclockwise. So starting at gamma 1 going downwards, and then gamma 3 also go downwards because we're going counterclockwise, and then gamma 2 going up, and then finally gamma 4 also going up. Now out of these, the gamma 3 is 0 because we're going straight up, so there is no dy. Okay, so dy is 0. And similar to gamma 4, there is no dy because we're going straight up. And then as a result, so we only have the gamma 1 and gamma 2 answers left. So as a result, then this is the answer, okay? And the total area, what we're calculating here is we substitute to P2 as f, then we get the answer of P2 will be equal to this thing subtracted by that thing. And what is this thing subtracted by that thing? That is exactly the equation 1 we looked at quite a while ago, okay? This thing that we derived earlier. And see, being that that's exactly that, and what is this anyway? This, as we have calculated, this thing is exactly the let's see, the other side, the integral over the entire border gamma, that gamma being the border of our x, is equal to this thing happens to be the negative of that. If you double check the two equations, then you see why. Oops, let me fix that. Oh, I should say that this is only a quick, this is just a repeat of the statement that's on top here. That is, I just copy and pasted this down here. The actual equation is actually minus phi, okay, and then minus psi and plus phi. So it's the negative of this stuff. So that is, in other words, this you have to slap a negative sign in there. So that is how this part is proved, and where now gamma is the entire border. So that is how we have come to the second part of the book. That is on the top of a second page. But this is just half of the proof. That is, what we did prove is this thing. That is, if we move down a little bit, that is, we proved that the green part is identical to the green part. And so the Green's theorem actually means that this part is equal to that part, and then this part is equal to this part. And the second part is proved in a similar way, which I also have here. Okay, now continuing, we'll do the Green's theorem part 2, where we prove now the Q part of the story. Okay, we have, see, the Q part will be equal to the Q part, just like previously we proved that the P part equals to the negative P2 part. However, the reason I do it again, you figure, well, that's just symmetrical, right? It is, but it's not that obvious. I feel like it's good that we go over the whole thing again. So by the same theorem, first we get to this part, and that's the easy part, okay? By the fundamental theorem, and of course the double integral is the iterated integral, which by the fundamental theorem we got to here, that equals to that thing subtracted by that, and well, that's so far so good. Now then we're doing the same thing here. But now we are considering our y. Okay, this is important. So we're looking at this sideways. In other words, tau 2 is this entire blue line. It goes from up here all the way to here. That's because the function here, okay, only has to, tau 2 will be called phi of t, or some, yeah. And the reason is because phi of t now only has to be continuous. See, it says right here, continuous only. It doesn't have to be differentiable. So tau 2 is only continuous, and then tau 1 in a similar way, okay, is equal to the psi of t, which is the first part, and then plus the other part, okay, both parts together, it becomes the tau 1, sorry. And the other one, the blue one is tau 2, which consists of two parts, okay, with a corner there. And so is tau 1, because now we're looking at this thing from the Ry perspective. So then the rest of the equations work out the same way. Please work this out yourself, okay? Make sure that I didn't make a mistake here. So then the integration now goes from, in the y direction, goes from c to d. And then, but we do the same thing here. We set y equals to t, okay, so then dy equals to dt, and then we come up with these two graphs. And so the next thing, we do a similar trick, then the integrating counterclockwise, again, around the border of now our y, we will have the first integral minus, which is gamma 1, which is going up, that's okay, but gamma 2 is going down, so we have to do the subtraction. Now considering now I copy and pasted the previous equation right here, okay, which substituting Q1 as, let's see, what is, give me a second here. It's right, never mind. So anyway, we have this situation substituting Q for F. Okay, so if we substitute Q for F, then this will be, and this together is the integral around gamma of Q. So that is how we got to this equation. See, the second one, you can say that is just like this first one, but not identical, okay? Specifically, you have to pay careful attention to the fact that now we have only two curves, and each curve has a potential corner there, but that doesn't hurt anything because our function is only expected to be continuous, nothing more. It doesn't have to be differentiable, smooth, or anything like that. So that is how the second part of the theorem is proved. So now we have finished proving the theorem. Now let's continuing on the next page, theorem 3, where we do the Green's theorem again. The difference here is that we have now the domain is defined with less restrictions. For example, consider the first sentence, okay? The R is a region of Rx, that's the same as before, and also a regular region. So it's also a regular region. Now, regular region is far less restrictive than the Ry business, because Ry is somewhat restrictive, okay? Regular is much better. Now, it only has to be Rx, so it only has to be in one direction that you can come up with an Rx, and then the rest, it just have to be regular, which is helpful in some situations. Anyway, gamma is again the boundary, and now P and Q are C1, which is the same as before, okay? And then we have So the same Green's theorem is supposed to apply in the same way that the integrals goes around the border is the same as Q1 minus P2 integrated over the area. Now to prove theorem 3, we notice that being that it is Rx, the previous proof, the Rx part still works. In other words, with Rx, we're able to prove that the P part equals to the P part. That is, we already know that this part equals to this part by the previous proof, okay? Because it is Rx, and that's how with Rx we're able to prove this much. So the question left is, how do we know this part is the Q part is the same? And that's what we're striving for. Now to do that, let's consider this region as an Ry, okay? And then well, sorry. Now the region we don't know if it's Ry, so we don't care about that. So, but we do know that gamma is a regular curve. All right. So then we will gamma then consists of four things. That is, being that it's still Rx, gamma is the boundary of this whole thing. In here is the Rx, okay, where we will call gamma into four parts, gamma 1, 2, 3, and 4, where gamma 1 is y equals to psi of x, going backwards. Gamma 2 is x equal to a, okay, going down. Gamma 3 is y equal to phi of x, going normal way to the right. And then gamma 4 goes up, is x equal to b. Now knowing that, then we can calculate the integral of qxy dy, which is equal to starting, your book starts here, but it doesn't matter how it starts. So what we're doing is go all the way around, and and plugging in this case, we plug in y equals phi of x, okay, which means dy equals phi prime dx, and that's how we are able to get the first one. This is the first integral here is the what I call gamma 3, and the rest are similar. The second integral is going backwards on the phi curve, okay, and this one right here. So similarly, phi prime dy equals to psi prime x dx. So you plug that in, and then the next one is we set x equal to b and integrating up, so it's positive. So we have a plus, this plus 1 over here. And finally, the last one is going down x equal to a. So you see that is integrating and then of course watch out for integrating limits. It integrates from phi equals to from psi of a to psi of b. What am I talking about? Let's see. From phi. Well, anyway, I should talk about the first one first. This is from the one we just talked about. This one, it goes from psi of b to phi of b, right? So that is what this checks out to be. See? And let's see, yeah, see, from psi of b on top to psi of b on the bottom. And let's see, I should move my hand, otherwise it doesn't focus. Okay, that is going down from this point to this point. And the other one then is going from, no, that was b, I mean from, well, anyway, from this point to that point, that's the B one. Okay, the other one's the A one from that to that. Anyway, please check this, go over this yourself. Okay, make sure everything comes out. And then so then the next thing we need to, so that sentence is taken care of. So the next sentence, the integral of Q1, we're focusing only on Q1, the Q's here. The double integral of Q1 ds, then as before, then it equals to, we can do the first part of the integration, being that is Q1. Actually, no, we can't. I forgot. I keep forgetting this is not our y. We can't use the same trick. But we can write it out as the integral from a to b, and then from the phi of x to psi of x, and that and then that part of the integration will be done as and dx goes from a to b, and dy goes between those two things. All right, so that's so far so good. So the next thing we're going to do is define big F of x to be exactly the integral on the inside. Okay, now if you do that, you'll be able to define some kind of a function of f, and that's fine. And then the next sentence, it says then in that case, then f prime of x equal to that big long thing. Now, we will accept that sentence for now, okay, instead of figuring out, because that sentence is proven 3 chapters later, and we're not going to look 3 chapters later. So we will accept this sentence to be proven later. And then now if we accept that f prime equals to that thing, then of course the part I marked pink happens to be identical, okay, and so this part equals to that part. Then what we're going to do is then we're going to plug this out of there. That is, we're going to take this out. That is, this then equals f prime x minus that plus that, okay, and then substitute this thing into this equation right here, this thing right here. So then if we do that, then the whole thing, I should write it out. I think I did. Okay, I have it written out right here. That is, the double integral is equal to this. That is f prime minus the other stuff, because that will, with the first integral still here, by substituting this thing in the equation of f of x. So that in other words, this thing here is equal to this entire long line, okay, by the equation of what f prime of x is. Now, once we've done that, then we'll do at this point, we can do the integration, well, some of it. For example, we can do by fundamental theorem that this thing is equal to f of b, okay, minus f of a, because we're integrating from a to b, and the rest of the integral will keep it as is. Now, if we do that, then we notice, what was the definition of f again? F is this thing. And so f of b is exactly let's see. I'll show it in the book. I think can see better. So f of b, okay, yeah, the book looks much better. So f of b is exactly this thing right here, okay, because of the definition of f. If you see the definition of f and plug b for x, okay, then f of b is exactly this one right here, okay? And then similarly, f of a is exactly this thing right here, where things are being plugged, x is replaced by a. So, and then minus these two things are the same as what we had before, and therefore the double integral is equal to the line integral, and we have proved what we were setting up. Okay, these two then are the same. So please look at this very carefully and until this all makes sense. The main trick is this sentence, which we will accept without question, and then you will isolate, substitute this expression in here, okay, and to get this thing. And once you get there, then you're good to go, and that marks the end of this section. So then also notice that our x can be replaced as our y in the hypothesis 1. So this, in other words, we proved it for our x, but our y is no different, okay, because it will work just as well. But that is, you have only one Rx or Ry requirement, and the other requirement is just that it's regular. So next, let's consider page 225, where the remarks says subsection 2.3. Now, if a regular reason, it can be divided into a finite number of regions Rx, and so you can cut it into chunks. Then equation 1 still holds where let's see, where's equation 1? That is the Green's theorem, okay, still holds where gamma is the total boundary, consists of more than one regular closed curves. So then, as long as you can cut it into a finite number of stuff, I guess everything can still work. The reason, as an example, then let's consider this donut-shaped thing, okay? And then, so what we do is, the thing itself is not Rx Is it? Well, it needs to be cut to be Rx, okay? Cut a finite number of times. In that case, and we will do the Green's theorem on each one, okay? And then calculate that goes around each one once. And then at the common border, it will go over in 2 different directions, so they will cancel each other out, and everything will come out nicely. And then so let's consider the next paragraph. That it can be shown that every regular region can be divided into a finite number of regular subregions. Okay, we're not going to prove that. Rx or Ry. Okay, so every regular region, finite number of subregions Rx or Ry. All right. However, it is so that equation 1 is valid for every regular region. So the Green's theorem applies as long as your region is regular, because every regular region can be divided into a bunch of Rx or Ry. However, it is not always possible to subdivide into a bunch of stuff that's both Rx and Ry. And then we'll see an example. And because of the inability to cut stuff that will fit both requirements, then Theorem 3 is therefore more useful than Theorem 2. Okay, because Theorem 3 is more inclusive. And then as an example of a region that cannot be cut this way, the book gives us the region Rx equal to 0, 1, x, what is that, cubed? X cubed sine 1 over x and 1. And if why is that one cannot be cut into Ry, then I drew this thing out. Okay, and then you can see that this thing is an Rx, but it has a complication at the origin. That at the origin, when you zoom it in, it just keeps wiggling forever. Okay, so in other words, any subregion that contains the origin cannot be Ry, which is what I said. Let's see over here. And because of all that, if you have to contain the origin, then it just too much wiggling, vertical wiggling up and down past the origin for you to be able to do anything about it. So that is why this is the case. So next, we will look at subsection 2.4, where we are trying to find area of stuff, okay, to apply for this. Now, to find the area of something, what we are going to do is use the Green's theorem, and we'll let either Q equals to 1, the other one is 0, or Q1 equal to 1, okay, and let P2 equal to 0, and that will give you a formula. Or let P2 equal to 1 and Q1 equal to 0 give you a different formula that looks like this. Okay, this is from when I think the dx one is from P equals to 1. If P2 equals to 1, then P equals to y if Q is 0. And then the other way, you get this formula, and then or you get half of 2 added together. So these formulas are good especially in the homework in calculating the area of stuff. Okay, and so that is here's an example A of calculating the area of the ellipse, and as you notice, it comes out very quick and nicely. Okay, just by substituting stuff quickly into the answer. So please do that yourself, and that is the end of this part, and we have come to the homework. So for homework, please do page 226. All the problems except 11, I believe. So go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 12, 13, 14, 15, 16, 17. Yeah, that is that. And when you're done, I want to talk about all of them. And I'll finish this video, this section in the next video.